Good afternoon, everyone. Today we have Nicola Gnecco from Imperial College. Welcome, Nicola. Thank you for giving a talk. You're going to talk about extreme of structural causal model. So the floor is yours, and thanks.
Thanks a lot for the introduction, Anna, and thanks, Emma, Nathan, and Anna for the very kind invitation. So I'm happy to be here today, where I'll talk about a relatively recent project that I worked on. And this is joint work with Sebastian Engelke from University of Geneva and Frank Röttger from University of Twente. Now, before starting, I want to give a high-level motivation of why even the project arose. And the motivation that we started with was trying to kind of describe mathematically, or a bit more precisely, the idea that the causal structure that one might observe in the extremes, in the tail of a distribution, might differ from what we are able to see in the bulk. So what I'm showing here, it's a very simple scatter of a data generated from the random vector x1, x2, where we simulate it from the following system. So this data is generated from what we call a structural causal model. So for now, don't worry too much about what it means. I will try to give a bit of intuition about this object. But the idea is the following. We have two variables, x1, x2. And the second variable is caused by the first one because it depends functionally on the first variable via the function f. Of course, if we had access to this function f, well, we could describe perfectly this relationship. And this relationship could be described even well beyond the training data that we observe, right? Now, the problem is that in practice, we cannot say much about what happens really at the boundary of the support or even beyond. And so the idea is really the following. Even though the function that we can kind of infer here seems to really depend on x1, so in the bulk of the distribution, we see that there is a causal dependence between x1 and x2. What we are trying to ask is what happens if we intervene and we actively set the first variable to a very large value, for example. And of course, what happens to the second variable will depend really on the full specification of f. As an example, we might have a case where this effect, so this f effect, dampens. And so we see here that the corresponding realization of x2, so once we set the first variable to a very large value, we might have a situation where the second variable kind of gets a value that is not far away to its marginal support, okay? And in such a case, we would like to say that in the tail, there is no more causal effect, like this effect from the f function dampens. But in other settings, we might also have this opposite. For example, we intervene on the first variable, we still set it to a large value, and now the corresponding value with respect to the second variable is very large. And in such a case, we would like to be able to say, at least as precisely as possible, that the causal effect kind of persists even in the tail. So this is really a very high-level motivation of what kind of started the project. And in the following, I will try to answer a couple of questions. So the first one is, how can we define causal models, structural causal models for extremes? So what happens in the tails? Now, what do these structural functions look like in the tail of the distribution? And under which condition does the causal structure change in the extreme? What do I mean by that? I mean that there might be the case that you observe data, and given the data, like what we saw here, given the data available, we would be able, in some cases, to infer some causal relationship between x1 and x2. But then this causal relationship actually disappears in the tail. In such a case, we might have really a simplification of the causal structure in the tail. And we want to be able to say under which condition this event occurs. Okay. Now, before starting to kind of explain what we contributed, I will make a small recap of this topic, which is graphical models in extremes. And to talk about multivariate extremes, it's important really to kind of set up a bit of a notation. So first, we define with this boldface x a random vector with the components. And the goal of multivariate extremes is really to study the joint distribution of this random vector when x is already in a state that is extreme. Now, of course, as you can imagine, now we are in, say, RD, so there is not kind of a clear order in RD. So what does it mean for a vector to be extreme? So there are like different possible definition of defining when a vector is large. One common definition of describing X in an already extreme state is when the maximum entry, so the maximum element of this vector exceeds a certain threshold, okay? So here to give an idea, suppose we are dealing with 2 dimensions, so also the notation simplifies a lot. Suppose that x1 and x2 are also standardized to some margin, because in the end, like what we want to understand is the dependent structure. So the marginals do not kind of can be filtered out in the first stage, and let f denote the CDF, assuming that the CDF of x1 and x2 are the same for simplicity. Now, what multivariate extremes tries to study is the following quantity, okay? So given that our vector is already in an extreme state, what happens to the probability of exceeding a very large threshold, okay? So here, tau is a very large quantile, and phi inverse of tau, tau is a quantile level that gets closer to 1, and phi inverse of tau is a quantile level on the scale of x1 and x2. Now, I want to give kind of an example to motivate why it's interesting to study this quantity and why is it even kind of possible under some assumptions. So what I did here, and this example is really taken from an idea from Chen Zhou, who's a professor at University of Rotterdam, is the following. So I just downloaded daily loss for 2 stocks, actually 2 indices, the FTSE and SPX, from 2010 to 2025. And I try to compute, at least empirically, this quantity over here, okay? And I want to see what happens as I push this quantile level higher and higher. So the first thing we can do, let's focus on the days when at least one of the 2, so the maximum of SPX and FTSE, are in the worst 5% of their days. Okay, these are the losses. So large values means large losses. So the values are actually all the values in this L-shaped region. And then we count how many joint crash we had when both SPX and FTSE are in their 5% worst. So here we really have this ratio. So 78 cases over 308, which is kind of the conditioning space. We have roughly 25%. We have, as an estimate of this conditional probability, 25%. Now we can really try to see what happens if we push higher and higher this threshold. If I do a 2%, of course, I get fewer observation, both in the L-shaped region and in the joint region. And I see that I still get a number that it's comparable, at least magnitude-wise. I can repeat this for higher and higher values. Of course, what we observe here is that there seems to be, at least qualitatively, a convergence of this quantity, of this distribution. Of course, with finite sample, if I'm going to push like higher and higher, eventually, this is not going to be even well-defined anymore because there will be no more data. But this behavior of the fact that there seems to be some stabilization of this quantity when we push the quantiles higher and higher when we study the tail, it's really the motivation behind this multivariate extreme theory, okay? So here it's really just to define the distribution that we're dealing with. So again, we start with a random vector, and then what we assume for simplicity that all its marginal are standardized to this exponential distribution. And now what we want to be able to say is the following: given that the maximum of X exceeds some threshold U, what is the shape of this survival function? It's 1 minus the CDF, if you like, exceeding U. And we want to say something about that when U, this kind of threshold, goes to infinity, okay? And it turns out that under kind of some condition, actually fairly mild, this quantity converges to the probability of a random vector Y exceeding a certain threshold. And this vector Y has a kind of well-defined distribution, which is called the multivariate Pareto distribution, okay? This multivariate Pareto distribution is actually a family, a non-parametric family of distributions, so it's pretty large. I will show how to kind of restrict and deal with some subclasses, parametric subclasses of this distribution. But the 2 interesting and important points to keep in mind are the following. So now, this random vector y that arises as a limit has a density that it's okay. You can think of this lambda y really as the density of this random vector. And the important thing to keep in mind is that this random vector now has a support that is L-shaped, right? Because we are really conditioning on the fact that the maximum is above a certain threshold, so we have this L-shaped region. Now, if we want, this is really about multivariate extremes. Now, the next question, in order to be able to define graphical models and therefore kind of causal quantities, is to say, is it possible to study conditional independencies of this random vector? And of course, as it is, it's not clear, right? Because in order to define any notion of independence, we usually, actually, we have to rely on vectors that live on rectangular regions, or also called product spaces, okay? So here it's not really clear how one could define notions of independence and even more precisely conditional independence. And this actually was kind of a problem that was solved in 2020 by a paper from Hengek and Itz, where their idea was the following, was really to say, okay, given the original random variable here, random vector, let's say it's in 2 dimensions, let's condition on one of the given dimensions that were given. Let's say y1 is larger than the threshold, okay? Now, conditioning on this event, we first see one thing, that of course we kind of simplify the problem, because now we are we have kind of a new version of the random variable, which I define here y superscript k, which is just kind of restriction of the original random variable on this rectangular space, okay? This, of course, might seem arbitrary, but it already buys us the fact that we are in a rectangular space, okay? I could also define another version of this random vector if I condition on the second coordinate, and I would obtain then y superscript 2 of this. Now, given this auxiliary random vector, what one could do is to use classical notions of conditional independence to really define the idea that 2 coordinates of this random vector are conditionally independent given the others. Why is this possible? Because, yeah, the support now of these random vectors, it's really a rectangular region, a product space, okay? Now, so far, I mean, this is something that can be done, but the question is, how does this relate to this original random vector that lives in this L-shaped region? Because it's the region that we want to study. And this was really kind of the remarkable result, because starting from this auxiliary random vector, one, of course, it's free to define, it's free kind of to compute conditional independence in the classical sense, but then one could say, okay, this notion of conditional independence clearly depends on k, on which variable we chose to condition on. So if we condition on the first, for example, or the second. So what if there is a contradiction? And actually, what turned out to be the case, and this is in this 2020 paper, is the following. So the remarkable result is that this definition does not depend on the variable on which you condition. And the remarkable reason is that the density of this random vector over here, it's still the density of the original random vector, which is kind of not given because now we are conditioning on this event, but only it's restricted in its support, okay? So really this definition, this kind of result led in this 2020 paper, which is kind of the background for our work, to be able to define a notion of conditional independence for the extremes. Because now, if we start again with this random vector y, bold y, which lives in this L-shaped space, we are able to say that some of these entries are conditionally independent given the others. For example, we could say that if A, B, and C are some subsets of this vector that are disjoint, we can say that yi is conditionally independent of yb given yc in the extremal sense. And we write it so with this subscript e to denote this extremal sense. If classical conditional independence holds for any version k of the random vector. So no matter somehow the direction you choose to with respect to conditioning, then you can define classical notion of conditional independence. Now, this notion of conditional independence for the tails was really the first step to open the possibility of describing, in a sense, graphical models in the tails. Because for those who might be a bit familiar, and it's not kind of fully necessary to get all the details like for the rest of the talk, but for those who are familiar, once we have notions of conditional independence in a random vector, one can really encode these conditional independencies via graph. So here the idea, for example, would be every variable in the vector is denoted by a node in the graph, and then missing edges in this graph. So if node I and j, so 1 and 3, is not present in, the edge between 1 and 3 is not present in the graph, this really means, if we have these graphical models, that the entry y1 is conditionally independent in extremal sense to the entry y3 given the rest, okay? And yeah, if you're interested to really learn or kind of read more about graphical models for multivariate extremes, I recommend to have a look at these review papers. Before going on, I see there is a question and maybe there are others.
Just need to understand the definition properly.
Sure.
That this conditional independence, it doesn't matter what k you pick.
Yes.
Here you work for all k and d, but it could be for some k and d. They will be the same.
Yes.
Exactly the same.
Exactly. And this really follows by this kind of special fact that the density of this kind of version of the random variable still has really the same definition, is just restricted on this kind of half space. Yes. Are there perhaps any other questions on this? Yeah, which was kind of background. Yeah.
I just wanted to understand.
Sure.
This, it feels like one could visualize this in a copula space, for example, two-dimensional setting.
Yes.
Is it easy to see what the copula would look like? Maybe it starts to just with independent uniform samples and some are the copula space.
But you mean in the tail, whether there is...
Yeah, exactly. So the tails would probably correspond to one quantile in bar.
Yes. Well, I don't know if it fully answers the question, and then I can maybe follow up. But actually, so this limiting random vector y bar, okay, follows this multivariate Pareto distribution. And this multivariate Pareto distribution allows for different types of asymptotic dependence. So what happens in the joint tail? So you could have cases where you have perfect asymptotic dependence or not. What we will restrict in this talk is fully asymptotic dependence, as I will explain in a second. It's mostly for technical reason, but yes, that's a very good point. Yes?
Sorry, so the question. If you can go back to the graph from the
Sure. Yeah.
page, right? And also, if I remember correctly, the existence of a curve distribution says nothing about where the actual limiting point is, right? So, are there any like funky restrictions around that?
The existence of
Like, I'm going off of like having seen extreme value theory once, but the theorem which guarantees the convergence to the general Pareto doesn't say anything about where the U is, right? So is that
how far it is? You mean?
Yeah.
Okay. Yeah, that's especially in practice. It's always kind of so for practical application, like choosing the right U, you can really see it as a kind of bias variance trade-off in the sense that, well, this theoretical results holds for like U going to infinity. So to have little bias, you eventually want to push this as high as possible, but then eventually you just have a few data points, and so the estimates of this will be completely uncontrolled. And so yeah.
I don't think I expressed my question correctly. Is like the result of extreme conditional dependence, like the independence, is it dependent on U? Like, is there any like does it say anything about U or no?
Well, as long as
isolated or
as long as you, at least in the first approximation, I would say that as U goes to infinity, well, then you have this convergence in distribution, and then this random vector y satisfies this notion of extremal conditional independence. But yeah, I'm not sure if this fully answers the question. I'm happy maybe if you want to take it offline. Yeah, offline. Yeah, thanks. All right. So the first thing I want to discuss, it's really the first kind of contribution we had, which was really how to define, to extend this notion of undirected graphical models in the tails to directed graphical models, okay? And this was actually, for those who might be familiar with the literature in graphical models, was kind of fairly straightforward in the sense the idea was to combine the existing notion of conditional independence in the extremes with definition of separation between nodes in a directed graph. Now, in a directed graph, a notion of separation is the one of d-separation here, okay? And so what we kind of came up, actually, it's really the mirror of the Markov properties in the non-extreme case, in the sense that now if we are given a DAG G and a multivariate Pareto distribution Py, then we are able to say that we define actually Py satisfies this extremal global Markov properties with respect to the graph if for all disjoint index at ABC, whenever the nodes A are d-separated from B given C in a graphical sense in our graph, this implies that there is a conditional independence in the extremal sense at this random variable there. Okay, then there is kind of similar notion with respect to the local Markov property, which says that each variable is, in this case, extremely independent of its non-descendants given its parents. And then there's also this factorization property that really says that the density, now remember the density of y bar, can be really nicely factorized according to the topology of the graph. So now we really need to, like in the non-extremal case, we can express this density as the product of simpler density where we just need to condition on the graphical parents, okay? And also here, as it happens when we have a density in the non-extremal case, these notions of Markov Markov notions or Markov properties are equivalent. So this is really kind of the first object that we defined. Now the second one, where I will discuss a bit more time, it's about how now it is possible to define also structural causal models for extremes, like for the tails. And before starting, I really just want to give a quick recap, at least at an intuitive level, of what a structural causal model is. And for today, I think like a fair representation also for you to keep in mind of a structural causal model, you can think of it really as a tuple of two objects. So first, we have a set of function or assignments and a distribution PE, in this case, a product measure, so over some noise variable, okay? And a structural causal model, as I will explain in a second, if we do not assume feedback loops, always induces a directed acyclic graph G, okay? So what I'm writing here is, of course, a specific example of a structural causal model where we have x1 only depends on the noise, x2 depends functionally on x1 and x2. For example, it can be linear, it doesn't have to be, this is just an example. x3 also depends functionally on x1 and so on. And we see that given this non-acyclic and recursive actually definition, we can also draw a directed acyclic graph that is induced by this, right? First, we have the four nodes, and then whenever there is a variable appearing on the right-hand side of this assignment definition, well, we draw an edge, for example, from 1 to 2, from 1 to 3, and then 2 to 4, 3 to 4, okay? Now, this structural causal model, as it is, might look like, okay, it's a data generating process, right? And it is true because in the sense, like if you go on R or Python and you sample data from this model, well, you will get kind of a scatter, or like if you sample infinitely long, you will get a joint distribution, okay, over this random vector X. But now what's special about structural causal model, or like what structural causal model allows you to do more than, like, say, plain data generating process, is that they also kind of assume or allow you to say something about how the system behaves when we change some part of the system, when we kind of intervene, okay? So for example, on this model, we can intervene by setting the first variable to a fixed value, let's say 100, okay? That is possible to do. What happens actually now is that we get a different assignment. Now it's f1 tilde that gets value 100. And what does this intervention does? Of course, creates a new structural causal model, a modification of the original one. And it also now induces a new distribution now that we denote by this 2x100. And in this case, for example, can be seen that this like fixing the value of x1 to 100, it's actually the same as conditioning on the first variable being equal to 100. This is not always the case. So, okay, we see that modifying this system really yields a new model that now I define by this x1 100, which is really defined now as a pair, again, of assignments and distribution over the noise. And we see here that what changes is the first assignment, okay? Now, of course, this new structural causal model will also have a new DAG induced, okay? In this case, nothing changes, right? The dependencies are all, the causal dependencies are all still there. But it might be the case, for example, that if we intervene on another variable, for example, let's say the second one now, what will happen is the following. So again, if we sample data from this, we get different distribution. And now, interestingly, this distribution, which is a do distribution, an intervention distribution over the vector, does not correspond to just conditioning on the second variable being 100. And the idea of that is that when we condition on the second variable being 100, we'll still have dependence between x1 and x2. Whereas here, by intervening, we really kind of destroy any sort of dependence. And this is why now that the new DAG, the new structural causal model under this intervention will be a new one that induces this new graph, which I denote by G tilde. So now we see that the edge disappeared, okay? So this is really all for kind of structural causal model, like without any reference to extremes. But yeah, I thought it was good just to fix a bit of intuition before defining what we try to do kind of in detail. And yeah, feel free. I don't know, I didn't ask the organizer if it's fine to ask questions in between. Yeah, so feel free if something isn't clear or... Yes?
Or in practice, for most data sets that one has, one would not actually observe X1, one would observe it with error.
Yes, that is.
So this presumably causes some problems when you try and impose this particular structure on things.
Right. Yes, that is a good point. So what I was trying to describe here, it's actually the ability, or actually the assumption that we make about these models, that they are able to describe not only data that kind of we observe from a system, which could be like this composition, this kind of configuration, but also the ability of these models to describe what happens to the very same systems when someone were able to actively intervene on it. It's possible, for example, in kind of medical trials where assigning treatments. Of course, what I haven't mentioned, this is not the only possible kind of intervention one can do. One can, for example, think of changing the assignment of the second variable by just randomizing, so putting some Gaussian noise. So replacing really the definition of x2 with some independent Gaussian distribution, and this would kind of amount in a medical trial to randomize a certain treatment to patients. Yeah.
So in a medical trial, you could do something like you could titrate a treatment dose.
Yes.
Until the observed blood pressure is at some particular level.
Yes.
So that would be an example of intervening with X1 in some way to fix X2. But the problem in practice is you won't observe the blood pressure without error. You will actually have.
Right. Yes.
It's not quite the same as what you would like to do, ideally.
That's a very good point. And of course, this is, if you like the first kind of approximation to define, or actually, no, that's the first definition of an SEM. And here, what I am kind of haven't said is that this doesn't prevent, for example, the possibility of having existing other variables that are not observed. And these would really cause this measurement error, for example. So this can be allowed for sure. In this talk, we won't consider that. So we assume that all the variables are kind of observed. But yeah, in confounded setting, yeah, that arises for sure. Thanks. Okay. So now moving to the extremal part, how can we define now this kind of structural causal model, but for the tails? And the idea is really to start with a classical structural causal model. So we are not in the extreme yet, which is M. It's a structural causal model over our random vector. And we assume that this induces a certain DAG, okay? Now, a few assumptions we want to make on this original structural causal model to study how it behaves in the tail are the following. The first one, and it kind of goes back to the copula question a bit, is to assume that there is a single root node to the graph. And the idea here is really we want all variables to become large at the same time. In other words, we want the system to be asymptotic dependent. It doesn't have to be, but the analysis kind of would be more technical because we wouldn't have a density in the tail, and yeah. So this is kind of the first assumption. Suppose we have this system that kind of is rooted in one node. And okay, the other kind of assumption, we suppose that the random vector we are dealing with, so this x random vector has already margins that are standardized. In this case, let's say to exponential margin, okay, for simplicity. And now this is kind of the important regularity condition that we have to make on the original structural function. We assume that the structural function, well, can be nonlinear, can have like different behavior, but in the tail, if we kind of evaluate this function for larger and larger value t, this function will eventually have some sort of homogeneity property, meaning that they will behave linearly in t plus some possibly nonlinear function psi that only depends on the fixed value x. So this is for some threshold t that increases. Now, having these kind of three conditions, so the structural causal model with one root and these functions that kind of behave following this homogeneity property in the tail, we can actually study what happens to the limit distribution of the original SEM. So remember, if I have a structural causal model, M over a certain vector, I can generate data and therefore it will induce a distribution. Now let's study what happens to its distribution, but in the tail. So what we do is the following. We condition on the first node, actually the root node, to exceed a certain threshold. In this case, it's called the threshold t. And then we want to study the behavior of the whole vector x bar over this threshold, okay? And now we want to study this probability as the threshold grows and tends to infinity. And what it turns out is that this random vector x bar condition on this event converges in distribution to a random vector, which turns out to be actually one of the auxiliary random vector that I kind of described in the beginning. So x1 now, y1 that arises as a limiting distribution is really the, if you want, the first auxiliary random vector of the multivariate Pareto random vector y that we saw in the beginning. So this result really tells us that if we have this structural causal model that kind of has this homogeneity property in and this one root structure, we can really say something about its kind of tail behavior. And even kind of more interestingly is that this limit variable itself will also satisfy kind of its own, if you like, structural causal model, which we call an extremal structural causal model, because it will have kind of some sort of different assignments, right? So the first variable, it's the root node, kind of remains standard exponential, so because it was all the margins were standardized to standard exponential, and this was just depending on the noise, the root node. But now all the other variables now are defined via these assignment psi, which were kind of the extremal assignments that we postulated in this assumption over here, okay? And now this new structural causal model for the extremes has a couple of properties. So the first one is that since it's a structural causal model on its own, it will induce a certain graph. And the interesting thing here is that the induced graph, which we call an extremal graph, will be a subgraph of G. So really, it means that in the tail, some of the kind of causal dependence can disappear, really formalizing in the sense the intuition in the beginning that we might have some causal structure in the bulk of the distribution, the one that we can kind of observe. But then eventually in the tail, this effect, for example, might dampen. And the second one, okay, is that these extremal functions themselves will satisfy the same homogeneity property of the original functions. Now, this remark, I would say it's only for those who are a bit more familiar with graphical models and causal models. So it turns out also that, given this structural causal model in the extremes, this satisfies kind of automatically the Markov properties that we defined in the first part. Now, I'll try to give a bit of an example. It's a kind of very simple one, but just to kind of anchor a bit of the intuition. And that is the following. It's a very simple structural causal model. Everything is linear, okay, except for the last assignment, where the fourth variable depends linearly on the second, plus this rational function, okay? Now, what happens to this random vector, or actually it's the behavior of the structural causal model as we let the first root node take in larger and larger values, okay? Of course, intuitively, you can see that these larger values that is taken in the first variable propagates downstream, right? Everything is linear and yeah. But somehow this rational function has an effect that it's kind of dampened more and more, right? Because when x2, x3 gets larger and larger values, then yeah, this term kind of becomes negligible. This is really like intuitive what's happening to the corresponding extremal structural causal model that arises, because this structural causal model will be such that actually the first three assignments are unchanged, so they're still kind of linear. Now the fourth one will also kind of simplify in a sense, because it will be now only a function effectively of the second variable plus the noise. And this really kind of encodes the fact that in the tail, the causal dependency between 3 and 4 disappears. This is, of course, one specific example where this can happen. But yeah, I think it was good just to see it, to get a bit of intuition. Now, this that I showed so far, it's really about what happens when we have this limiting random variable that is kind of a multivariate Pareto distribution. But as I said, the multivariate Pareto distribution is a family of distribution, a non-parametric family, meaning yeah, it's very rich. So what one can do is to kind of restrict the attention to a subclass. And this subclass, it's kind of quite nice to work with. It's called a Husserl-Rice distribution. So it's a family of distribution which are parameterized by some matrix called like precision matrix theta. And these can really, this Husserl-Rice distribution can really be thought to some extent as the analog or the corresponding of the Gaussian in the non-extremal world. And what I'm trying to show here is the following, because if all these extremal assignments that arise in our system are linear, and this noise term, except for the first one, which has to be kind of exponential, if all these noise terms are Gaussian, then this resulting, the limiting random vector y, boldface y, will follow this Husserl-Rice distribution. And okay, so far so good. You might say, okay, why do we care? And the interesting thing is that this Husserl-Rice distribution, as I said, is parameterized by this precision matrix. And this precision matrix, like it happens for the Gaussian, really encodes somehow conditional independencies between the variables. Now, conditional independence is not in the classical sense, but in the extremal sense. So this is kind of interesting, because really, if one restricts attention to this parametric subclass, then one can try from data by looking in the tails to learn this precision matrix and say something about which variables are conditional independent really in the extremes. This I will show kind of some ideas on how one can use these facts for learning the graph structure in the tail. Okay, so in the last, I think roughly 10 minutes we might have, I want to discuss first how one can define on this. Now, okay, we have described how this structural causal model in the extremes can arise. But then the second question is like, is it possible to define some sort of intervention in this structural causal model, and how this intervention behave? Are they completely different from what we are used in classical causality or not? So I'll try to answer this really a bit kind of pictorially and with some examples. The first bullet point is really recalling what we are talking about when we talk about intervention. So here in causality, when we deal with perfect intervention, we are really substituting the assignment for a certain variable to a fixed value. Of course, this is not all possible intervention one could do, but it's kind of a specific type of intervention, okay? And doing this intervention really modifies the assignment, right? We modify the assignments from FV, whatever it was, to fixed value. Now, the question we try to answer is, what if we intervene to some variables, but by setting them at a very large value, okay? And the spatial example of intervention we consider here is an intervention that we call an extremal intervention that is made of this kind of T, which is kind of a threshold that we move larger and larger plus some offset, okay? And what we want to understand, as I said, is how this intervention behave in this causal model that arose in the tail, okay? So again, the setting is the following as before. We start with the structural causal model, not in the extremes, okay? Now, on these causal models, we can define certain type of intervention, and we concentrate on this type. So if we set, for example, one xv to a value t, which can grow, and psi v, and then we want to understand exactly what happens to the resulting extremal SCM. And what I drew in this picture that looks a bit daunting, I will try to explain, because it's really kind of graphically, it's kind of roughly a commutative graph, what we're trying to explain, right? Because what we started so far, what we started with, like in the beginning of the talk, was this normalized structural causal model. So there is no extreme involved here. And in the first kind of result that I showed is the following: what happens to the tails of this random vector if we really look at the root node exceeding some value and we study kind of the whole random vector. And what we saw is that in the limit, this non-extremal structural causal model converged to what we define to be this extremal structural causal model. Okay, but so far no interventions involved. But now what we're trying to do is the following. So we start again with this causal model. First, we kind of perform some intervention, and this we know how to do because we are still kind of not in the tails. We fix some value t, we fix some value psi v, and this really modifies our original graph, our original SCM to a modified one, okay? So far nothing kind of special. But now, okay, this random vector, it's indexed by t, okay, because we perform this specific intervention. And now the question is the following: what happens now to this random vector as this threshold t is really set larger and larger? So as t diverges, what happens to this random vector over here? And this is what we define to be the intervene extremal structural causal model, okay? And so in a sense, we want to define intervention in the extremes via this kind of path over here. That was, of course, not the only way to do it. It was kind of a possible way. And I'm sure like there are like other ideas to explore here. And yeah, happy also to hear any thought on that. And of course, instead of kind of giving kind of formal results, I think it's just easier to see an example. So suppose here, again, we start with our model as before that induces this graph. And now suppose that we intervene on the first node. We intervene in this kind of extremal sense. So far it's still kind of classical SCM, just intervened one. Now, of course, what happens if we let t grow? Well, this variable will become large, and via this homogeneity property, we'll see that also all these variables x2, x3, x4 will become large. And so if we study the behavior of this random vector above t, this converges to like the structural causal model in the tail that we had in the beginning. The only difference now we can see is that instead of having exponential noise, we really replace by this fixed value to which we intervene, okay? So this is kind of not super surprising, but kind of the first step we observe. Now, what can happen in another example? Okay, what happens if we intervene on both node 2 and 3? What happens in the extremal structural causal model? Now, as you can see, as we let this t, this threshold, grow larger and larger, well, this t will propagate downstream, right, causally. And so x4 will grow, but in a sense, the first variable is kind of left behind. So when we study the limiting behavior of this random vector above t, we will see that the resulting SCM kind of looks a bit different from what we're used to do when we kind of perform intervention on classical models, right? Because here we see that these variables are kind of replaced by their offset value to which we intervened. The descendants of this variable kind of do not change their assignment, but every non-descendant of the variables that were intervened, well, we see that kind of are, in a sense, left behind. So we allow them here, we define them to be like, to take value minus infinity. And the last example, again, to give a bit of intuition, suppose now we intervene only on 2. So again, of course, the fourth variable will receive kind of downstream this increasing effect. So if we keep setting t larger and larger, this will propagate downstreams. But of course, the non-descendants of 2, so the non-descendants of the variable that are intervened will be, again, left behind. So that's what will happen in the intervened SEM in the tails. And then as a side note, which is, I think, also interesting to keep in mind, what happens to the fourth variable? Okay, the psi doesn't change, right? Because 4 was not intervened on, and it's a descendant of 2. However, depending on the specific form of psi, we might have kind of different evaluation. For example, if psi is defined to be the maximum of y2 and y3, well, in this case, we have the maximum between psi, which is a real number, and minus infinity. So we will get psi 2. Vice versa, if we had the minimum function, then we would have evaluation that like really sets the fourth variable also to minus infinity. So this is just to highlight the fact that these structural causal model in the tails have, at least for this specific type of intervention, a slightly different behavior from what we're using kind of in classical causality. Okay, in the last, it's actually, 3 slides, I just want to give a bit of an idea of one could possibly try to learn these objects. And these ideas will build actually on much of so the heavy lifting, in a sense, has been done by the classical causal community. And the first way to possibly try to learn something about this extremal structural causal model is by exploiting the PC algorithm. PC algorithm, for those who don't know, it's a very popular structural learning algorithm in causality. And this PC algorithm in the non-extremal setting requires, in order to kind of estimate, actually, it's called a Markov equivalence class, so which is kind of a or completed partially directed acyclic graph. So to estimate this object, which is kind of, you can think of it as a graphical object, you need some conditional independent statements, okay, to run the algorithm. Now, what one could do here in the extremes could really run the classical PC algorithm, but replacing the classical conditional independent statements with extremal ones that were defined at the very beginning of the talk. Of course, this entails estimating these objects, but this is, for example, possible if one restricts attention to the parametric subclass that I introduced. So if we study the Husserl-Rice, then it is possible to first estimate the precision matrix, theta, and then from the precision matrix, one can infer or read off these extremal conditional independencies in a similar way that we're able to do in the Gaussian case, where we estimate the precision matrix there, and the zeros kind of correspond to missing edges, okay? And then, given this idea, of course, one could potentially apply the PC algorithm as usual, and one would recover the CP DAG, okay? Which is basically a DAG where some edges are not directed. Now, the second idea instead stems from the fact that, as I mentioned in the beginning, what might happen in the tails is that some of the causal connection might disappear, okay? So the idea is the following: why don't we kind of try to exploit the fact that maybe there exists already, maybe in some domain, we might already have a kind of a hunch for some sort of causal structure. In some domain, for example, there are like well-established methods that work in the non-extreme setting. And so the idea would be the following: what if we start with kind of an initial guess for the graph? And this graph, it's really the graph that pertains the system in its kind of non-extremal state. And then, so for example, we start with an SEM with a certain graph. And then, since we know that the graph in the tail will always be a subgraph of the original one, not necessarily a strict subgraph, but a subgraph, then we can really try to prune this graph using, again, ideas from conditional independence testing in the extremes, okay? So for example, in this case, starting from this graph, we could test whether 3 and 4 disappear in the tail or 2 and 4, okay? And of course, in practice, what one could do, again, by restricting to Husserl rise, one could try to estimate this precision matrix and use some sort of parametric partial correlation test. For this, it's actually what we also used in the article, like we tried on some simulated and real world data. But just as a caveat, so far as I know, there are no kind of theoretical results on this test for the precision matrix in the Husserl rise. I think it's much kind of ongoing work, and people are trying to establish like asymptotic distribution for these objects. Now, in the last example, and this is really illustrative, what I want to show, it's really kind of this idea of pruning. So suppose we are in a setting where we collect data over a river network, okay? And now these little dots are really different stations along the river network. Actually, this is a branch of the Danube kind of basin, a part of the Danube basin. And well, what we know in this example, it's nice because it's data collected at different station, and at this different station on a daily basis, we collect the level of the water. And what we also know is that given the topology, we can draw really the causal graph of how the water flows, right? Because it flows kind of downstream. So this is kind of the ground truth that we are kind of trying to see whether we are able to recover to some extent. And now one idea is really, this is to test out like this pruning idea, is to say, okay, let's start with a full graph. And this full graph is really so-called kind of the transitive closure of this graph. So basically we connect all stations to their kind of downstream stations, okay? So this clearly, it's much denser graph. And what we want to see is whether, just from the data, if we estimate this precision matrix for the Husserl-rise distribution, and then we perform conditional independence tests on this, whether we can prune some edges by looking at higher and higher kind of threshold, okay? So what we do here is the following. So we start by really estimating this precision matrix from the Husserl-rise distribution by really keeping the top 10% of the data. So we fix the tau level at 90%, and we see that already kind of some edges gets pruned. And then we see what happens if we kind of push higher and higher this quantile. So we basically look closer and closer into the tail. And what we observe, at least qualitatively, is that kind of most of the edges disappear, but also kind of in a positive way, what we recover, it's still kind of a super graph of the true one. And for in particular, we see that no kind of true edges are deleted. Of course, this is just a qualitative example, so one would need to kind of test much more thoroughly. But I think it's kind of an initial indication of why this might be interesting. Like in the main article, we also compared the same approach of pruning using classical notion of conditional independencies. And interestingly there, the pruning with like using classical conditional independence tests, it's working like much less effectively. Like for this data set, it might be the case that, you know, you have to think these stations are, well, far away, but still from the same region. So for example, if you have kind of a huge rainfall in this region, well, you have some sort of confounding effect, right? Because of course, whenever there is large kind of water level upstream, this will propagate downstream eventually. But of course, if you have also a heavy rainfall, this affects multiple stations at the same time. But somehow, like looking at the tail seemed to help in this regard. But this is really kind of a first step towards like investigating how this model can be learned from data. Okay, so to wrap up, what we defined today is extremal graphical models, directed extremal graphical models, structural causal models, and intervention on these causal models for multivariate extremes. We propose two possible ways of learning these objects from data, and these are based on conditional independencies geared towards extremes. And kind of the key idea that we started the project with, and we tried to make a bit more formal and precise, is that kind of the causal structure that occurs in the extreme can differ and oftentimes simplifies compared to what happens in the bulk. So if you're interested, yeah, the preprint is on arXiv, and I'm very happy to take questions. Thanks.
We have one question online.
Yes, that's me. Hello, can you hear me?
Yes, hi.
Hello. Hello also everyone. If you basically test conditional independence in the extremes, right? There may be two possibilities, right? One possibility may be that really there isn't much causal relationship anymore if you go to the extremes, which is basically what you're interested in. But another possibility is you have less data in the extremes. And if you have less data, then tests have less power, right? In particular, that means you will test based on a smaller data set, and that even if nothing changes, will give you a larger probability to not find significance there, right? So it could be hard to tell these two things apart, don't you think?
Yeah, thanks for the question, which is a very good one. And I totally agree with you. So in the article, we try to study a bit, at least heuristically, whether this is the case. And I think it's kind of true in the sense that in general, it's hard to disentangle these two effects. The fact to, the loss of power because we have fewer data, and because, okay, this is for those who are maybe not familiar with conditional independence testing, like if we fail to reject, we prune. Basically, the null hypothesis is that two nodes are conditionally independent. If we fail to reject, so if we don't have a lot of power, we fail to reject often and we prune a lot. So this is certainly a problem. What we try to do, and of course it's definitely not a full answer, but we try to compare on comparable sample size what happens to non-extremal conditional independence tests. And there seemed to be some sort of additional pruning made by the one that we used here. But again, this is based on experiments and heuristics. In terms of theory, as far as I know, that would be a very good question to answer.
Thank you.
Yeah, thanks a lot for the question.
Yeah, thanks. Was that Christian Henning, by the way?
I think so, but I haven't seen.
Yes, absolutely. Hello.
Okay.
Hi. Stephen Sen here. So that was very interesting. Thank you very much.
Thank you.
I'm sort of worried because usually as a statistician, you're taught you should be very, very careful about looking at extreme values because they may be very unrepresentative in some particular way. And here I assume that it's not worth doing unless you think that the causal relationship is somehow importantly different in the extremes than it is for the distribution as a whole. But there are some occasions where I think if you start doing this, you get very misleading results. I'm thinking of Bergson bias, collider bias, this sort of thing. For example, you might find among actors that the more talented they are, the more they earn, and also the more good-looking they are, the more they earn. But if now what you do is you select high-earning actors, what you actually find is that the correlation between looks and talent is negative, although in the population of actors as a whole is zero. Yes. Precisely because you have to be either good-looking or talented, yes, in order to be a high-earning actor. So is there any danger in what you're doing here that you actually introduce side effects which are dangerous for your conclusions?
Well, first of all, thanks for the question. I think it's a very good point, and what reminds me, it's actually the following. So what I have discussed today, in a sense, it's a very specific type of causal modeling, which we have a kind of a single root node. And so all the system somehow has some sort of dependency in the tail, which means that all the variables are highly dependent, statistically speaking. Now, the example you were bringing, I'm not sure, maybe I might have misunderstood, but what I have in mind, it's really the classical collider example, yes, where two variables are independent unconditionally, but then when we condition on one, like it must be because one of the two kind of has a very large value. I think that would be a very interesting kind of configuration to study in the extremes. And in a sense, what we have done here doesn't cover it, because we're really considering systems where when one variable gets kind of a very extreme value, all the others kind of follow. And that's why kind of we also use this kind of river stream example, because it's kind of one work and it seems to lend itself quite well. But in such case, yeah, I think it's an open question, and there are many applications where it would be very important to be careful about that. So yeah, thanks.
So we are running a bit out of time. Maybe we can take this last question online, and then we can go all upstairs for a cup of tea and additional questions. David, do you want to ask your question now?
Yes. I'm a bit puzzled about how you distinguish between extremes and outliers. I am pretty skeptical about the literature on outliers. I think none of it works. But can you enlarge on that a bit?
Literature on outlier or extremes or both? Because
if you're dealing with real data, how can you tell if it's an extreme or an outlier?
Okay, let's say that I think it starts from two different kind of questions that one tries to answer, because with outliers, we really try to identify points that are kind of different from the bulk of the distribution. So it's really kind of a detection problem. And one can assume in some, at least outlier literature, one can assume that such points are generated by a perturbed version of the original distribution. But here, at least in the extreme value theory literature, the assumption is that kind of the distribution F of our random vector is fixed. But the problem is that we get finite amount of data, but still we would like to be able to say something about very small probability events. And of course, like without any assumption, that might sound like magic, but then there are these kind of limiting results that tell, like the ones that I introduced in the beginning about this multivariate Pareto convergence, that really follows from like probability theory results. And they can be seen to some extent as the central limit theory counterpart, but for the tails. So as we often kind of assume that, I don't know, the sum of independent variables tends to be Gaussian, like here it's like assuming, okay, we have a finite sample, but then if the sample size grows and we look farther and farther into the tail, then there is this probabilistic convergence that tells us that the tail will follow this multivariate Pareto distribution. But at least the way I view it is outlier-based literature and extreme value theory literature have a bit of a different kind of goals. But I'm happy to like discuss further.
Well, thank you very much.
Thank you for the question.
Thanks. So we can all go upstairs for a cup of tea and rest of the questions.